any element has a high atomic number, even if we consider something like greater than 100, the value of A, we do say that it's quite high. But then does it fission on its own, or spontaneously? Does it happen like that? The answer is no. And this is something which we are going to express more. Okay, we are going to understand it better now today. So in the last class, I said that what the question might be, what is the minimum value of A for which the fission is said to be energetically favorable? So whenever we are going to talk about something like energetically favorable, we are talking more or less about the Q value. So if the Q value is positive, it's energetically favorable. If it's negative, the reaction cannot happen, right? So we just assumed that we had two nuclei A, and it fissions into two different nuclei of A by 2 and A by 2, and then we actually went into the definition of mass defect. Okay, and we did understand that mc square is equal to this. So this is something which you have done a number of times. So really don't need to explain that part. Okay, and then we do have the binding energy, and we saw in the binding energy, out of the uh, 5 terms we actually have, one term we are ignoring, the pairing energy, because we are considering an even system. We say that the volume does play a role, okay, because we have got the volume term as the first term when we are talking about the binding energy, right? But then here what happens is, we're talking about fission. One nuclei separates into two different nuclei, but then the total volume does not change. So that's why the volume term is not considered here. Okay? Thirdly, we took about the surface term, and we do know that if we have two nuclei, the surface area increases, so surface term will have an effect. The Coulomb term also plays a role, because if you're talking about two nuclei which are having positive protons there, if they are separated out, the Coulomb interaction comes into effect. Within the same system, the proton-proton will mostly exist as nuclear interaction. Okay, but then when they are separated out, there is Coulomb interaction resulting. So whatever result we are going to get for the activation energy or the binding energy will primarily depend on the surface term and the Coulomb term. Okay. In asymmetry term, we know that n becomes n by 2, z becomes z by 2, a becomes a by 2. If we just do it, it will more or less remain the same. So this is what we have seen in the last class. Okay, and then based on this, we did some calculation. What we did was this. Okay, so in the last class we did find out what was the rest mass energy, and we compared both sides. Okay, for before and after the reaction, and we saw that for this reaction to happen, the Q value, which is nothing but mc square minus 2m square, should be greater than 0. That is what is the definition of Q value is. That is where we actually say that the reaction is possible or energetically favorable. So if you do this and do a bit of maths, put the constant value of surface term and the Coulomb term, what we see is that the value of A should be greater than 100. Okay. The question is that if it is greater than 100, does it mean that there will be fission? The answer is actually no. Why? This is something which we are going to look into today. Okay. So today what we are going to see is the Bohr-Willa theory. Okay, so today we are going to see the Bohr-Willa theory. So Bohr and Willa has explained this, and that's why it is basically called the Bohr-Willa theory. Okay, so before we really proceed, let's just look into a bit of theory here. So what happens is this. Okay, we have the idea that yes, if it is heavy, there will be fission, and Bohr and Willa said that this fission is not possible for any atomic system which basically has more A. So there are some restrictions, and they took the help of the liquid drop model. Okay, so in order to understand how the fission happens, we are going to look into this. So the liquid drop model we have come across. Okay, we have actually known about the semi-empirical mass formula, which was also derived from liquid drop model. Liquid drop model is something which we have not discussed in detail. Okay, but then the idea is very simple. Okay, if you just look into the theory part of it, that we do have the nuclei. Okay, and then let's say there is no separation. Okay, let's say we have this, and this is the center of that nuclei. Okay, and then this R is equal to 0. Now as some energy is put in, what happens is the nucleus, because you see, if you want to actually separate out a nuclei into two parts, there has to be some energy. So if that energy comes out from within the nuclei, that is spontaneous. But then if you are allowing some neutron or gamma ray to be incident on the nuclei, and then their nucleus splits into two, that is more or less, we can say, induced, okay, induced fission. So what happens here is that if we put some energy, there are stages by which the nuclei actually gets splitted. Okay, so the first stage might be it will actually slowly turn into something like an oval shape. So if you remember ellipse, okay, you know that there are two focus, right? So there are basically two centers which are possible. So what happens here is that this center starts to deviate. So we will have slight deformation here, okay, and that deformation is written as R, okay, and this R is basically called the deformation parameter, okay. This is the R is the deformation parameter. Then the next stage is that the nuclei actually starts to wobble out. They are not yet separated, but then the distance between the centers keeps on increasing. So this is there, this is there, so it has increased, so this is R now. And then what happens is the deformation is more, it slightly gets more, it's on the verge of a breakup, okay, it's on the verge of breaking up. So it will be like this, and again the deformation parameter will be there, okay, and then finally it breaks. So it's already broken, okay, but then there is still some kind of interaction, okay, there is still some kind of interaction, and finally they are far apart, okay. So at this particular position, what happens is we have got the Coulomb interaction. Now what happens is we have only the Coulomb interaction that is working between them. So here it was the nuclear force, here it was the nuclear force, here it was the nuclear force, even here it was the nuclear force, okay, and the energy was uh, overcoming the nuclear force. Once the nuclear force is overcome, it breaks into two, and finally they are into two different parts. And this is what the liquid drop model says, okay, this is what the liquid drop model says. So what happens is the underlying idea that we should not forget is the volume remains the same. The volume does not change, and this is the uh, property or feature that we are going to use to actually understand it mathematically. So the volume remains the same. So this was the beginning of the Bohr-Willer's theory of nuclear fission. Okay, they did take help from the that of liquid drop. Then they tried to explain it. So if we just look into this, okay, what is this energy that we have based on which there will be some deformation, okay, and how it is basically calculated, okay. So if you just look into this, okay, so what is the energy for each deformation? It was calculated, okay. Energy for each deformation was calculated, and you know that if there are different values of A, depending on how many number of nucleons are there, depending on that, this energy will vary, okay. So this is important. So let's look into this from this point of view. So initially, when everything was within the system, okay, it's basically a nuclei. So there is q value that exists, okay. So we have got the relation, or we can actually plot a graph between energy and distance. So if you understand this graph, half of the work for today's class is done, okay. So probably I'll just concentrate on this graph at the beginning now. Let me just explain it. So what happens is this: you have the sorry, so you have this plot between the distance and the energy. So when the deformation parameter, this R is nothing but the deformation parameter is talking about. So we don't have any kind of deformation that we made. That means there is no separation between the centers. So if that is the case, the energy is maximum for the system. Okay, and then you know what happens is that as this centers keeps on separating, there is a separation between these points. The energy keeps on increasing. Okay, and at that some point the energy will be maximum. The energy will be maximum. And if that nuclei is able to separate itself out, that means it has overcome that maximum energy. Think about it in this way: you have let's say you have got some kind of ball, okay, some kind of ball made up of some kind of material, might be some kind of sticky material, okay, and then you want to separate out that ball. You want to separate out, or you can break, you want to break that ball into, so you'll apply some energy, and you'll hold it, okay, and you'll try to pull it apart. And the moment at which it tries to get separated, you will realize that at that particular point you are applying maximum energy. So just before it breaks into two parts, maximum energy is applied, okay, and this is what is happening here also. So the logic is this, okay, this remains the same. So if we consider this as the baseline, the energy when there is no nuclear separation, and the point at which exactly the nucleus is about to separate, this particular energy is called the activation energy or the barrier height. This is the same barrier height that we understand from quantum mechanics. This is the same activation energy that we basically have come across before also, okay? So if you want to activate a nuclear reaction, you basically need to put in some energy, and that is the activation energy, okay? Barrier height in general is you want to overcome that potential. So if you're considering a quantum mechanical well, and if you want to take the let's say a particle within it out of it, okay, you have to overcome that barrier height, you have to overcome that potential, and that is the barrier height we are talking about. So it does happen that we have a nuclei and it cannot break into two. That means the energy that is there within the nuclei is not sufficient enough to overcome this barrier height. So that means the spontaneous reaction or the spontaneous nuclear fission that we are talking about might not happen. Okay? That's the underlying idea. So if we basically consider a nuclei, typically let's say a nuclei which is having the value A as 240, the activation energy will be around 5.5 to 6.5 eV. Okay, so that means the barrier height that the system has to overcome is this 5.5 to 6.5 eV. Okay, so that happens, and then what happens is, see, if you go into this graph further, here we have the nuclear force which is acting, and the energy that is present within the system, okay, is trying to overcome this barrier height. But as soon as the barrier height is overcome, the energy that is working now is nothing but the Coulomb energy or the Coulomb interaction. So that's why here, after it has come out of the nuclei, that means the two nuclei has actually separated out, there is Coulomb force acting. Okay, so that is important. So you know that Coulomb force means we are talking about the two nuclei, okay, not the entire atom. So we do have, let's say the first nuclei has got Z1 number of protons, and charge of each proton is E, so it is Z1 E, and the second one is Z2, again charge is E, so it is Z1 Z2 E square divided by 4 pi epsilon naught R. Okay, so this is the energy that we are talking about here. Okay, so this is the Coulomb force that is acting. So if you look into this graph here, we are talking about the nuclear force. As soon as it has overcome the energy barrier, we are talking about the Coulomb force. Okay, at the beginning it is nothing but the Q value of the reaction. Okay, and Q value of the reaction is actually determined or estimated when there is no deformation parameter. The deformation parameter is 0. Okay, so if what happens is, if the nuclei are going further and further and they are very far apart, okay, theoretically we do know that this charge interaction will exist up to infinity. Okay, if they are at the charge, the field is there up to infinity, but for all practical purposes the field will vanish. So if we are having uranium, barium and krypton, okay, it it's there, the Coulomb interaction is there when they are nearby, but then if they are going very far away from each other, this energy will more or less become zero. So when the fragments are widely separated, the Coulomb interaction for all practical purposes is basically considered to be zero. Okay, so even if you keep that, you'll see that the effect is minimum. Okay, so this is what is important in this diagram, and this explains a lot of things here. Okay, so we are talking about energy versus deformation parameter. So for your exam purpose, probably you have to draw this diagram, try to remember what I explained, okay, and try to understand it, and from there you can answer a lot of questions. Okay, so just make sure that you understand this figure, that's important. And Okay, so that's there. Let's look into some more mathematical part here. Okay, so the fission, I think I don't need to explain these words, but anyway, just have a read through whatever I've explained just now. Okay, so if we actually want a fission reaction to happen, if we actually want a fission reaction to happen, this had to get through the barrier. Okay, the activation energy. Okay, it has to overcome that. Okay, for separating the nuclei. Okay, now because of this barrier, we actually have a stable and unstable nuclei for A greater than 100. So if we are having this barrier height very high, okay, when A is greater than 100, okay, and all of these things also depends on what kind of pairing energy is there any kind of asymmetry and so on, okay, it depends on that. Based on this, this barrier height is determined. So if the barrier is too high and the energy within the system is not sufficient, it's not going to give you fission reaction. So there will be no fission reaction. Okay? So that is important. So based on this, we basically have the fission reaction happening and not happening for any nuclei, okay, for any number of A. So the nucleus basically at the ground state will have an energy, let's say E dash, and it will split up into two parts. Okay, and when we talk about the energy of the splitted nuclei, it will be more or less different. Okay, and the rest mass energy will definitely reduce. We are going to look into it more. Okay, we are going to look into it mathematically also. That's important. Okay, so the intermediate state will actually uh, undergo the remaining energies between E dash and E double dash. So the energy that is there at the beginning and the energy that is there at the end, okay, after the nuclei has splitted, you know, after the nuclei has splitted, then also there will be some kind of energy which will be released. Okay, kinetic energy will be carried out by these two nuclei. Okay, the energy will vary between these two, okay, E dash and E double dash. But then this last 2 points we will actually see into it later. Okay, we're going to look into that part. But before we proceed, let's just have a clear understanding of the mathematical part, and then let's just look into the volume thing. Okay, so imagine you have the nuclei, okay, and at the beginning when there is no separation, okay, we are still into the liquid drop model. If there is no separation, the volume is 4 by 3. Okay, the volume is 4 by 3 pi r cubed. Okay, but then once it starts to deform, okay, and their center starts to separate out, okay, you will see that this A, which is actually was R initially, and this R, whether you take it along this direction, the x-axis, the y-axis, or the z-axis, will remain the same. But then after it has started to deform, these values will change. So let's say along the x-axis, in general, if you consider an elliptical region, we talk about the semi-major axis. But please remember, this is not a two-dimensional picture. This is a three-dimensional picture. So we do not really consider the semi-major or the semi-minor axis. Okay. So we just say along the x-axis, it is elongated. So A is more now, okay, compared to R. So now if I want to find out the volume of this, I will be writing it down as 4 by 3 pi, that will remain the same, into A, one of the dimensions, x, and then y and z. So y and z will say that it will remain as B. Okay. So this will remain the same for the simple reason that the volume will remain constant. There is no change in volume. Okay. So if we just cancel this out, we simply get r cubed is equal to ab square. Okay, but then what is A? We are not saying that, let's say this is the second stage, okay, this is the first and this is the second stage, and we are not saying that this R has changed too much. This R has changed by a very small quantity, R epsilon. Okay, so that means A, which is the R after it has started elongating, would be nothing but R plus R into epsilon. So epsilon is a very small quantity. Okay, so it has changed by a quantity of R epsilon. Okay, so let's just get back to this again. So we can again write down R cubed is equal to A, and A can be written as R into 1 plus epsilon. So we can write it down as R into 1 plus epsilon into B square. Okay, so please remember A is slightly larger than R. So what is my B now? B is nothing but R divided by root over 1 plus epsilon. So this is not something which should be very much difficult to understand, because this is not what is said by physics. Okay, this is more or less mathematical in nature. So what do I see here is that if R increases by an amount of R epsilon, by a very small amount R epsilon, this epsilon might be 0.001, 002. Okay, it's not even 1. Okay, it might be in decimal places. It's not that it's getting doubled. Epsilon is not R. If it's R, then R becomes twice R. That's not the case we're talking about. So if R increases by R epsilon B, okay, B, that means, or in general, let's not write down R, we can also say A. Okay, A increases by R epsilon, okay, or the radius changes by R epsilon. The B will decrease by 1 by root over 1 minus 1 plus epsilon. So you see, the relationship is not linear, that if this increases by a factor of, let's say, 2, this will reduce by a factor of 2. No, that does not happen. This is something which can be seen from this mathematical relation. Okay, so this idea has to be clear. Okay, and it's a straightforward idea, but then if you understand it, this is more easy. So then the question is, we can now calculate the increase in surface area and decrease in Coulomb energy. Why increase in surface area? Because you know that this one nuclei is going to break up into 2. So we know that the surface area is going to increase. So what we are doing is we are calculating the increase in surface area. And if they are getting more and more separated, at some point they will go very far from each other. So that means the Coulomb energy is reducing slowly. Okay, even if they are very close to each other, there is nuclear energy which overcomes the Coulomb energy. But as soon as the separation starts, the Coulomb energy slowly starts to come into the picture. And if the separation becomes more and more, the Coulomb energy will start reducing. And if they are very far, the Coulomb energy will almost come to 0 for all practical purposes. Okay, so that's why we say that what is happening is, with this process of liquid drop model, as the nucleus starts breaking into 2, there is an increase in the surface area, and then there is a decrease in the Coulomb energy. That is what is happening. Okay, now the calculation is a bit tedious. Okay, and we are not doing it. Okay, again, it's mathematical and we are not doing it, but in general what I say is, this is the surface. Okay, so the surface area will increase by this epsilon is there. Okay, this is the same epsilon that we are talking about. Okay, we are going to consider that radius. So surface area will increase by this quantity, 1 plus 2 by 5 epsilon square, and so on, the higher order terms. Okay, but then the higher order terms can be ignored. Okay, because this is epsilon is very small. If you take 0.1, it's okay. Then you take 0.1 square, it becomes 0.01. 0.01 cubed, you take 0.001. So I'm not going to consider the higher order terms. Higher order terms are more or less ignored. So this is the surface area increase. Okay, so if you look into this surface term, we are going to have this as 2 by 3 into 1 plus 2 by 5 epsilon square, and so on. But then the Coulomb term is going to reduce. Okay, the Coulomb term is going to reduce, the Coulomb energy is going to reduce. So this Coulomb term, after the separation starts happening, we are going to have it in this form. Here also we don't consider the higher order terms. We can just consider the term up to the second order. Okay, these things I think we have done a number of times, should not be very difficult. Okay, so what we can do now is, what we can actually try to separate out. Okay, so you know that I told you in the last class also that whenever this happens, the fission, okay, there is always a competition between the surface energy and the Coulomb energy, and depends which term overtakes which one. Okay, if the surface time overtakes the Coulomb term, that means we are more or less moving towards the fission reaction. Okay, so if we just look into this, then there we can actually find out what is the increase or what is the change. Okay, I think with change would be a good term. What is the change? So we can just subtract the one term from the other term. You see, the first term is here, that does not put any effect because that was there originally. If you look into the change is this. Okay, this into this, that means this part. Okay, changes this part into minus the change in this part. Okay, change in this part. So we can subtract one term from the other. Okay, and then we see what is the change. Okay, and what we want is that this energy change should be less. Okay, this energy change should be less. So it means that if we have a slight deformation, it should reduce this energy so that the binding energy is less. Okay, now why we want actually the binding energy to be less? Okay, so we want actually the nuclear fission reaction to happen. Okay, so if there is too much variation between the surface term and the Coulomb term, okay, the binding energy will actually vary. Okay, the binding energy is going to have an effect on the system. So if we want to actually have less binding energy, the chances of nuclear fission will be more. The nucleus can actually separate out them, right? So for that, we are actually doing this. So if we want to want the binding energy to be less, this term must be less than 0. So if you look into the original term, we have the volume term, we have the surface term, we have the Coulomb term. Okay, and if the effect is only because of the surface term and the Coulomb term, which is actually subtracted from the volume term, which is the only positive factor, if that subtraction is less, okay, we know, okay, that the binding energy is playing a role there, okay, because these things will affect the binding energy, right? Okay, so try to understand this here, that when there is a slight deformation, it should reduce this energy so that the binding energy is less. Okay, and this happens when this particular term is less than 0. Okay, this particular term is less than 0. Okay, so we have these two terms. So what are the things that you need to remember is probably this. Okay, this is there is a lot of calculation here, so I don't want you to remember the calculations. It becomes a bit difficult. Okay, become too long. But then I just can tell you that you can remember these two terms. It's not very difficult. You have to just remember the second order term. This one you already know. This one also you already know. But this term you should know, and this term you should know. Okay, one is subtracted. We are talking about the Coulomb term because they are getting separated out, and the surface term increases because this is getting increased. Okay, that is important. So we soon do have an assignment. Okay, so I'll probably put one topic from this also. So try to understand it. You have to show your understanding also, very important. Okay, so then this particular term should be less than 0. Okay, and if we just do the maths here, see this 2as, okay, minus z square by a into ac is less than 0. Okay, so if we just do it, okay, you can take a to the power 2, a to the power 1 by 3 plus a. Okay, oh sorry, minus a. Okay, or you can just take it a to the power 1 by 3. Let me just do this here. Yeah, it's okay. What we can do is we can basically take an LCM here. So if we take a to the power 1 by 3 as the LCM, we can just multiply it here. So 2 by 3 minus 1 by 3 will remain only 1 by 3. Okay, and then you can get a 1 by 3 here. You take common, you do the maths. Okay, just take the take it, multiply it with 0, and then the final term which will be simplified would be this 2as minus z square divided by a into ac is less than 0. Okay, so this calculation I have not done. I leave it up to you. I think this is okay. Once you do this, this is less than 0. It simply means that z square divided by a is greater than 2as divided by ac, right? Please remember there is a minus sign before this z square. Okay, so if you take it on the other side, it will become z square divided by a is greater than 2as by ac, or in simple words 2as by ac is less than z square by a. Okay, so if we put the value of, let's say I'll put the value of a as a 16.4 and put the value of ac as 0.72. Okay, you know Coulomb term that the value is minimum. Okay, you can always remember this. So once we put these two, okay, once we put these two, what you can have is the value as nothing but 47. So if you do this maths, you see that z square divided by a is actually greater than 47. So what are the possible values of z and what are the possible values of a for which this will be greater than 47? Okay, so if we do just bit of trial and error, okay, if we just put some random values and try to find out this, it is observed. Okay, this can be done mathematically, but we are not going to put everything there. We are just going to go into the final conclusion. We can always do the experiment and we can actually do the calculation. But then if we just put some values, let's say I put the value of z as 0.4a, that means 0.4 times the mass number. Okay, and if we put that value, we always find out that a is greater than 300. So here we can put 0.4 into a, Okay, so this will be 0.16 into a square. That a will get cancelled, and then you can do your maths. Is greater than, so this a is greater than 300. What does this tell me? This tells me that any material, okay, any element whose mass number, okay, or the value of a is greater than 300 will undergo spontaneous fission. That means it's going to have fission on its own. Okay, and that is why this is shown mathematically. So do we do understand that if you consider something like plutonium 239 and a value, okay, one of the isotopes, or uranium, let's say 235, 236, 238, they does not undergo fission on their own. We do have to give some energy, maybe in the form of gamma ray, or more commonly, which you know is in bombarding with neutrons. So you bombard uranium with neutron, then only it undergoes fission. So if we just go back to the basics, we know about fission. So we do know about nuclear reactors. And then we say that we bombard the uranium with neutron and then it undergoes fission. But then in the last class, we did see that if something, the A value is greater than 100, it should undergo fission on its own, spontaneous fission. That does not happen because of the Bohr-Wheeler idea that we have seen just now. Okay, but then again, if we look into the Bohr-Wheeler idea and try to analyze it mathematically, we do see that the value of the mass number that we have should be greater than 300. So this also proves that uranium cannot go undergo spontaneous fission because its mass number is below 300. So if we actually make a man-made element, okay, let's say whose mass number is greater than 300, okay, then it will undergo spontaneous fission. So you know, stability is a very important part if you want to actually look into the element of the periodic table. So if it is stable, that means the mass number is not that much high. Okay, so there is always this competition between the Coulomb energy and the surface term, the surface energy. And if we do have a system whose barrier is very high, okay, it cannot overcome that nuclear interaction. So as a result of which it cannot undergo spontaneous fission. So it's not that it's a one class thing. Okay, I've told you in the last two classes and you understand. No, you have to understand what is binding energy. You have to understand what is Q value. You have to understand what happens in the binding energy curve. All these ideas together will actually make more sense. Okay, so I have to think about everything, okay, before you really understand the topic. So we have covered every topic by now, okay, to understand what exactly happens with fission. So this is what is the advanced part of fission is all about, okay. This is the advanced part of fission. So what happens is, in general, if we are basically considering a neutron, okay, and it is, or let's say a gamma particle which is actually exciting a heavy nuclei, okay. So what happens is, if somehow, okay, we are creating a nuclei with a greater than 300, okay, we are creating a nuclei than 300, that particular nuclei will undergo spontaneous fission, okay, as there is no potential barrier, because it will have enough energy to easily overcome that potential barrier, okay. But then if we look into any practical purposes and we actually want to have a fission reaction, we do something which is called the induced fission. So what we do is we allow some external particle to be incident, okay, to make the system unstable, and as a result of which it will have enough energy to break into two. And this actually can be triggered even by a gamma photon, depends on what kind of system you're considering. So if you're having a unstable nuclei, okay, it's not very stable, okay, it's unstable, but still it is not undergoing nuclear fission. What you can do is you can just initiate the fission reaction by allowing some gamma radiation to fall on it. Okay, so we may have a element A and we are allowing some gamma radiation, and then this will become A star. So star, you know, it shows an unstable nuclei and it will basically undergo a fission. So this is basically called a photofission. Okay, so you understand this, that fission doesn't mean that I'll take uranium and I will allow a neutron to fall on it, and that is the only example of fission. Okay, but then what happens is, this is important because if you're considering a nuclear reactor, you need to use minimum element or minimum uranium to generate more energy, and that is possible by bombarding uranium with neutron, and that is why that is more popular or more common. But in order to understand fission, we can also say that we apply some, give some energy, external energy, and then the nuclear fission happens. Okay, So experimentally, this activation energy actually can be measured, okay, and even if we don't have any additional neutron or proton, okay. So this is more easy to do because we don't have an additional neutron or proton, so the activation energy can easily be measured, okay, so that is possible. So if you are basically considering a uranium system, okay, or if you are again taking a general example, we have A, and then we are bombarding it with neutron, and then we have got an unstable nuclei which undergoes fission reaction. So uranium 235 bombarded with neutron becomes uranium 236 and undergoes nuclear fission.